Chapter 5.3 is a continual discussion on binomial distribution. So if you recall from 5.2, binomial means two outcomes. Those outcomes are success and failure. We talked about N being the number of trials and R being the number of successes. So we will be continuing using the binomial table that I introduced in 5.2. So the first thing that we're going to look at doing is the graph or graphing a binomial distribution. So this graph is a histogram. So if you remember, a histogram is a bar graph in which the bars touch. Each R or each success is in the middle of the bar on the horizontal axis. So successes go on the horizontal axis. And then the probability of each of those successes goes on the vertical axis. So what we want to do is we want to look at a graph. So what we are given is that N equals 5, so this is my number of trials, and the probability of success on each individual trial is 0.6. And it wants us to create a graph. Well, notice it doesn't tell me what R is. Well, that is because we need to find the probability of each R. So my vertical axis will be the probability of R, or the probability of my individual successes, and then the horizontal axis, let me adjust that, here we go. The horizontal axis will be those successes. Okay, so if we have 5 trials, then that means I need to consider that R, or the number of successes, could be 0. You could have 1 success, 2, 3, 4, or 5 successes. So we need to look up each of these probabilities on our binomial table. So we know N is 5. So on my binomial table, I'm going to come down here where N is 5, and we're interested in all of 0 all the way to 5 successes. And so this is in the second pink, and I'm going to go up to where the probability of success is 0.6. So it's the second pink. So we would be looking at these values here. So here's the probability of 0 successes, 1, 2, 3, 4, and 5. So I'm going to write each of those into my notes. Sure, yeah, it looks like that's okay. So we have 0.010, 0.77, 230, 346, 259, 078. So these values, the successes, are on the horizontal axis. 0, 1, 2, 3, 4, 5. Those are going to be my bars. My probabilities, because each of these are P of R, and those are what we're going to put on our vertical axis. So let me see, 0.346 is the largest, so I'm going to go 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, 0.35. All right, so 0.010, 0.77, 230, 346 259 and 078. So that's what the histogram would look like. I would typically then title it, but we have no idea what these numbers represent, so there's really not a title that I can give. Now we have a histogram. If you recall back to the distribution shapes, this one could cause a little bit of problem. We know it's not bimodal. We know it's not uniform, so it's either going to be skewed or symmetrical. Now, if this bar was not here, it would be symmetrical. Here's the middle, and then two that are more or less the same on both sides. And I can understand why someone would choose this to be symmetrical. I can see that argument. But because there's this third bar, so here's my tallest, I have 2 bars to the right, 3 to the left, I would state this is more like skewed left. All right, now back in, back in 5.1, we found the mean and the standard deviation of a probability distribution, not a binomial, just a probability distribution. And here, let me move this. The formulas we used were these, and if you recall, it took a whole lot of work to find the mean and the standard deviation. That's for a probability distribution. Now we're going to find the mean and the standard deviation for a binomial distribution. And the formula is a whole lot easier. But you have to be able to distinguish when you are calculating just a probability distribution or a binomial distribution. And of course the binomial is when you use the table. So the formula for the mean, and remember, if you see the word expected value, you know he's asking you to find the mean. All you have to do is take n, the number of trials, times p, the probability of success on each individual trial. The standard deviation is the square root of n times p times q. So you can see it is a whole lot easier formula than the one we had to do in 5.1. So let's look at some examples that you would see that will have you apply those formulas. When Taylor shoots field goals in basketball games, the probability he makes a shot is 0.45. Okay, now, in this, I first typically go to n and I go, well, it doesn't tell me anywhere n. Well, if you come down here to the first question, it says out of 6 shots. So the trial is 6 shots, so the trial would be each shot. And you have the number of trials is 6. Well, success would be that the shot is made, so made shot. And it tells me that the probability that Taylor makes his shots is 0.45. So then failure would be missed shot. And we know P and Q have to add up to 1 because they're complements. So Q would be 0.55. So then, when the question says out of 6 shots, what is the expected number of goals Taylor will make? The thing to remember is when you see expected number, you know it is asking you to calculate the mean. So this, since this is a binomial distribution, we have n, we have success and failure. Since it's binomial, then I know all I have to do is take n times p. And n was 6, p is 0.45, and when you multiply that, you get 2.7. So what that tells me is anytime Taylor takes 6 shots, because that's what we're talking about here, when Taylor takes 6 shots, I expect him or her, I know a boy named Taylor, I know a girl named Taylor, I expect Taylor to make 2.7, so anywhere from 2 to 3 of those shots. The standard deviation is the square root of N times P times Q. And my comment on this would be, a lot of times students neglect to take the square root. So, actually I like the multi-view calculator a little bit better, so I'm going to, so the square root of 6 times 0.45 times 0.55, and we get, I'm going to round to 2 decimal places. Again, if you're on WebAssign, pay attention to that, because if you round it to 2 decimal places and it asks you to give 3 decimal places, it will be counted wrong. So I'm going to go 2, so it would be 1.22. All right, a second example. In a pharmaceutical trial, 60% of the men tested remained bald. So the 60% goes with remaining bald after using Rogaine. The cream will be tested on 5 men who have male pattern baldness. How many men do you expect to remain bald? Okay, well, when I see that they tested on 5 men, then I know my number of trials is 5, which means the trial is each man. Now, they gave me 60%, and they're asking me, how many do you expect to remain bald? So this 60% is the probability of success. So in this example, success would actually be remaining bald, which means failure is not remains bald. And of course, these have to add up to 1, so that would be 0.4. And when I see that it says, how many do you expect, I know it's asking me to find the mean. So it's saying, of these 5 men, how many of them would you expect to remain bald after using Rogaine? So since this is a binomial distribution, I take N times P, which is 3. So I would expect 3 of the 5 men to remain bald. Now, this question did not ask me to find the standard deviation, so I don't have to. If it did, then I would. All right, the next example. A dealer considers a car to be successful if it doesn't require repairs covered by warranty. If the probability of a car being successful is 80%, and what do they say success is? Doesn't require repairs. Find the mean and standard deviation for the number of successful cars among the 3 cars sold in one day. So the trial number of trials is 3, and 3 what? Cars. So the trial is each car. Success, and it used the word success, and successful means doesn't require repairs. And this occurs 80% of the time. So failure was needs repairs. And of course these have to add up to 1, so that would be 0.2. Now this one asked me to find both the mean and the standard deviation. So the mean is N times P, and 3 times 0.8 is 2.4. Now if it asked me to find the mean, then I would give my answer as 2.4. But basically what that is saying is 2 to 3 of the cars sold in one day will not require repairs. The standard deviation is the square root of N times P times Q. And again, don't forget to take the square root. So 3 times 0.8 times 0.2. So if I round to 2 decimal places, approximately 0.69. All right. Now, the last thing discussed about binomial probabilities is what is called unusual values. Now, recall back when we talked about Chebyshev's theorem, and this tells us that no matter what the distribution looks like, so it means any distribution, uniform, symmetrical, bimodal, skewed left, skewed right, at least 75% of the data will fall within 2 standard deviations of the mean, because Chebyshev's tells us 75%, 2 standard deviations away. So just to give you a little bit of a visual, I'm going to create a number line. So if this is the mean, then it's telling me that within 1, 2, so plus 2 standard deviations, and to the left would be minus 2 standard deviations. So here, within 2 standard deviations, it is telling me 75% of the data would fall between these 2 values. Now, for a binomial distribution, it is unusual for the number of R successes to be lower than mu minus 2.5 standard deviations. So here's mu minus 1, 2. Here would be 2.5. So anything lower, so it's saying anything out here would be considered unusual. And anything higher than mu plus 2.5 so this would be considered unusual as well, which means the likelihood of those successes would not occur a lot. It would be unusual to see those successes here. Not to say it can't happen, it's just not as likely. It is more unusual. So where you would apply this as an example, consider a binomial experiment. So it is important to recognize that it's binomial with 20 trials. So I know n equals 20, where p, so the probability of each individual success is 0.7. The expected number of successes is 14. Okay, there's that word again, expected, and expected is the mean. Well, previously we had to calculate this, but it is giving that value to me. So the expected number, or the mean of successes, is 14, and the standard deviation is 2. So it's asking what number of successes would be considered unusual, and here's what would be considered unusual. Now, you don't have to draw a number line. I just, for my visual learners, like to give them a little bit of something to lean back on. So if this was the mean, that's 14. So if the standard deviation is 2, that means as I go to the right, I would add 2. And as I go to the left, I would subtract 2. Now, 75% of the data, because of Chebyshev's, is within 2 standard deviations. But this is asking me what would be considered unusual. So unusual is plus 2.5 and minus 2.5. So anything lower than that, higher than that. So to find those values, then, unusual would be anything lower than mu minus 2.5 times sigma, which is 2. And when you take 14 minus 2.5 times 2, that gives you 9, which makes sense. If this is 8 and this is 10, then 2.5 would be 9. So anything lower than 9. And anything higher than would be 14 plus 2.5 times 2, which gives me 19. Which again, that makes sense because 18 and 20, so half of that would be 19. So anything smaller or any R successes, so 0, 1, 2, 3, 4, 5, 6, 7, 8, anything higher than 19, these would be unusual successes, not very likely to happen. That completes chapter 5.